We make the only car that would be considered sort of a real car, where
Right.
you can take it on the roads and that kind of
Some
thing.
have like a range of 15 or 20 miles. They're like,
Being able to do a software update and have several million cars suddenly go from
Fossil fuels, it appears, are about to become just as antiquated as the name suggests. Imagine a world where the vehicles we drive and the machines we rely on run not on fossil fuels, but on the most abundant element in the universe, hydrogen. This is not a theoretical idea either. Some of the greatest minds of our time are pondering about it. For example, longtime critic Elon Musk has conceded that this new water engine, which runs on hydrogen, will destroy the entire car industry. So what should we expect? Let's find out. The present and future of hydrogen technology.
Autonomous, are these things really going to be a reality?
autonomous cars will definitely be a reality.
During an interview with Auto Express back in 2015, Elon Musk famously dubbed hydrogen fuel cells as fool cells. He argued that hydrogen was an inefficient and impractical energy solution compared to battery electric systems. This criticism was natural, given Musk's position as the CEO of Tesla, a company pioneering battery electric vehicles and heavily invested in lithium-ion technology, which directly competes with hydrogen fuel cells in the clean energy sector. However, Musk's stance on hydrogen may not be as rigid as it seems. SpaceX, his aerospace company, has relied on hydrogen as part of the fuel mix for its rockets, such as using liquid hydrogen in some systems for upper-stage combustion. So how come he changed his mind about hydrogen fuel cells? And does this also reflect a change in the market mindset as a whole? Well, let's find out. Hydrogen fuel cell technology has recently witnessed notable advances. While hydrogen-powered vehicles have yet to match the penetration of battery electric vehicles in the market, they offer unique advantages that make them highly attractive for various applications, from passenger cars to heavy-duty trucks, buses, and even airplanes. One of the most remarkable advances in hydrogen fuel cell technology has been the improvement in fuel cell efficiency and durability. Initially, fuel cells faced several technical barriers, such as high production costs, limited energy density, and short operational lifespans. However, breakthroughs in materials science and manufacturing processes have drastically reduced the cost of producing fuel cells while improving their overall performance. Proton exchange membrane fuel cells, for example, have become more efficient, with newer catalysts being developed that reduce reliance on precious metals like platinum. Additionally, advancements in hydrogen storage have made it possible to store hydrogen at higher pressures or in liquid form, which increases the energy density and ensures a greater range for vehicles. But that's not all. Hydrogen has a higher energy content per unit mass than lithium-ion batteries, making it a more efficient fuel source for vehicles, particularly for applications requiring long range and high energy output. For instance, while a typical EV battery may weigh hundreds of kilograms to achieve a certain range, a hydrogen tank for a fuel cell vehicle can store the same amount of energy in a much smaller, lighter space. This is particularly advantageous for long-haul transport. Another significant benefit of hydrogen over EV batteries is the refueling time. Hydrogen fuel cell vehicles can be refueled in a matter of minutes, similar to the time it takes to refuel a gasoline or diesel vehicle. This is in stark contrast to electric vehicles, which typically require hours to recharge, even with the use of fast-charging technology. The rapid refueling time makes hydrogen a more practical solution for industries where downtime is costly, such as freight and transportation sectors. This feature also makes hydrogen more suitable for regions with large-scale fleets of commercial vehicles, offering a more efficient alternative to charging infrastructure that may not yet be fully developed in some areas. Beyond passenger vehicles, hydrogen fuel cells are gaining traction in a variety of heavy-duty vehicle applications. The truck and bus industries stand to benefit greatly from the advantages hydrogen offers over batteries. Long-haul trucks, which often need to travel hundreds of miles without stopping, require a fuel solution that can provide extended driving ranges without adding excessive weight. Hydrogen-powered trucks are already being deployed by companies like Hyundai, Toyota, and Nikola Motors. These hydrogen-powered trucks can carry heavy loads for long distances without the need for lengthy refueling breaks. Similarly, hydrogen-powered buses offer zero emissions, a key benefit in cities trying to reduce their carbon footprint and improve air quality. Cities like London, Tokyo, and Shenzhen have already incorporated hydrogen-powered buses into their fleets. The aviation sector is also showing increasing interest in fuel cell technology as a means to reduce its carbon footprint. Hydrogen-powered airplanes could be the next frontier in sustainable aviation. The aviation industry is one of the most difficult sectors to decarbonize due to its reliance on high-density jet fuel and long-range capabilities. However, several airlines and aerospace companies are exploring hydrogen as a viable alternative for both short-haul and long-haul flights. ZeroAvia, for example, is developing hydrogen-electric aircraft, while Airbus has been testing hydrogen-based propulsion systems, with plans to launch the first commercial hydrogen-powered aircraft by 2035. These efforts are still in the early stages, but demonstrate the potential of hydrogen to reshape the aviation sector by reducing or even eliminating emissions. So how come some industry leaders are skeptical? Elon Musk's evolving perspective on hydrogen fuel cells. Elon Musk has long been an outspoken critic of hydrogen fuel cells, famously referring to them as fool cells in the early years of his career. In an interview with Autoblog, he dismissed hydrogen fuel cells as a flawed technology. He argued that hydrogen's low energy density, the complexity of hydrogen production, and the expensive infrastructure required to support hydrogen-powered vehicles made it a poor choice compared to electric batteries. Well, this is understandable, considering that this was back in 2015, and the fact that he has a vision of a fully electric future. His company's focus is on advancing electric vehicle technology. But times and perspectives are changing fast. Despite Tesla's dominance in the EV market, lithium-ion batteries still face significant challenges in terms of range, charging times, and resource dependency. While EVs have made remarkable progress in recent years, batteries remain heavy, expensive, and reliant on minerals like lithium, cobalt, and nickel, whose supply chains are fraught with environmental and ethical concerns. The global race for lithium is intensifying, and the extraction of these resources can have a significant environmental impact, leading some to question whether relying on lithium-based technologies is truly sustainable in the long term. Another issue with lithium-ion batteries is the range limitations. Despite improvements in battery technology, long-range electric vehicles still require substantial charging times compared to gasoline or hydrogen-powered vehicles. For heavy-duty trucks, buses, and long-haul flights, the energy density of current lithium-ion batteries may not be sufficient. There is increasing recognition that no single energy source can solve all of the world's transportation and power needs. While Tesla has focused heavily on electric vehicles and energy storage through lithium-ion batteries, Musk has been exploring hydrogen as a potential fuel source for certain applications. His other company, SpaceX, uses liquid hydrogen in specific applications within its operations. For instance, hydrogen is considered for upper-stage rocket engines in the aerospace industry because it provides an exceptionally high specific thrust per unit of fuel, making it ideal for pushing spacecraft into orbit or propelling them through space efficiently. While SpaceX primarily relies on refined kerosene combined with liquid oxygen for its Falcon rockets, hydrogen's energy density and clean combustion are key advantages for certain advanced aerospace applications, such as deep space missions. Elon Musk's preference for hydrogen in the context of space exploration stems from its practicality in environments where efficiency and weight are critical. Hydrogen's low molecular weight allows for higher exhaust velocities. Moreover, hydrogen can serve as an energy storage medium in space habitats or fuel cells, making it a versatile resource for future Mars colonization, a long-term goal for Musk and SpaceX. However, hydrogen's use in rocketry does come with significant challenges, including its cryogenic storage requirements, high cost, and difficulty handling its low-density nature. Despite these hurdles, SpaceX has been exploring the integration of hydrogen in specialized contexts. Before we move on to how hydrogen or water engines will challenge the EV industry, let's take a look at the technical aspects first. The science of hydrogen fuel cells. Hydrogen fuel cells use electrochemical reactions to convert the chemical energy stored in hydrogen into electricity. This electrochemical reaction occurs when hydrogen gas reacts with oxygen to produce electricity, water, and heat. This process takes place in a specialized device called a fuel cell, which consists of several components: an anode, a cathode, and a membrane that separates the two. When hydrogen gas is supplied to the anode, it is split into protons and electrons by a platinum catalyst. The protons pass through the membrane to the cathode, while the electrons are forced through an external circuit, creating an electric current that can be used to power electric motors, homes, or industrial processes. On the other side, oxygen is introduced at the cathode, where it combines with protons and electrons, forming water and releasing energy in the form of heat. This process is fundamentally clean because the only byproduct is water vapor, making hydrogen fuel cells a zero-emissions technology, ideal for decarbonizing sectors like transportation, energy generation, and even heavy industries. The absence of harmful emissions like carbon dioxide, nitrogen oxides, or particulate matter makes hydrogen a key player in the global fight against climate change. Moreover, combustion engines typically operate at around 20 to 30% efficiency, as much of the energy is lost as heat during the combustion process. In contrast, hydrogen fuel cells are much more efficient, with efficiencies often ranging from 40 to 60% when used in vehicles. In fact, some high-temperature fuel cells can even reach 65 to 70% efficiency. Despite the significant promise hydrogen fuel cells hold, there are several challenges to their widespread adoption, primarily revolving around cost and infrastructure. One of the most notable barriers to scaling hydrogen fuel cell technology is the cost of platinum, which is used as a catalyst in the fuel cell's anode to facilitate the splitting of hydrogen molecules into protons and electrons. To mitigate this, researchers are actively exploring alternatives to platinum or strategies to reduce its usage. For example, the Department of Energy's Fuel Cell Technologies Office in the United States has funded various initiatives to explore non-precious metal catalysts, such as nickel, cobalt, and iron, which are more abundant and cost-effective. In some cases, platinum alloying techniques have been employed to reduce the amount of platinum required without compromising performance. The idea is to bring down the cost of fuel cells and make hydrogen technology more accessible to the mass market. Moreover, unlike gasoline or electricity, hydrogen is a low-density gas that needs to be stored at extremely high pressures or very low temperatures, such as in cryogenic storage. This requires specialized high-pressure storage tanks or cryogenic vessels, both of which are expensive to manufacture and maintain. Additionally, the development of hydrogen refueling infrastructure remains a key hurdle. While traditional gas stations are widespread and relatively inexpensive to build, hydrogen refueling stations require a substantial initial investment in storage and compression equipment. According to the International Energy Agency, hydrogen refueling stations are still limited in number, with less than 500 globally. A potential solution to the storage issue is the development of solid-state hydrogen storage, where hydrogen is stored in a chemical form, such as metal hydrides or ammonia, which is safer and more efficient than current methods. Researchers are also investigating liquid organic hydrogen carriers as a potential solution for easier storage and transport of hydrogen. Despite these challenges, there is a growing consensus within the scientific community that hydrogen fuel cell technology is key to achieving a clean energy future. Significant progress has been made in improving the efficiency and cost-effectiveness of fuel cells. Moreover, as global interest in hydrogen accelerates, hydrogen fuel cells will become more accessible to consumers. For instance, Toyota's Mirai and Hyundai's Nexo are two examples of hydrogen fuel cell vehicles that have already entered the market. These vehicles are powered by fuel cells that offer longer ranges and faster refueling times compared to battery electric vehicles. In the industrial sector, fuel cells are being deployed in areas like backup power systems, material handling, and remote power generation, with companies like Plug Power and Ballard Power Systems at the forefront of developing commercial applications. The maritime industry is also looking at hydrogen as a potential fuel source for ships, with companies like Ceres Power and ABB working on hydrogen-powered marine propulsion systems. Potential global impact of hydrogen-powered vehicles. As governments and industries alike strive for cleaner alternatives to fossil fuels, hydrogen vehicles offer a transformative opportunity to reduce greenhouse gas emissions, replace traditional fuels, and reshape industries, urban landscapes, and infrastructures. Traditional internal combustion engine vehicles, which run on gasoline or diesel, are significant contributors to greenhouse gas emissions, particularly carbon dioxide, nitrogen oxides, and particulate matter. These emissions not only exacerbate global warming, but also degrade air quality, leading to a host of health problems. In contrast, hydrogen fuel cells only emit water vapor as a byproduct, making them a zero-emission solution at the tailpipe. According to estimates from the International Energy Agency, the transportation sector accounts for roughly 14% of global carbon dioxide emissions. Naturally, hydrogen's potential to decarbonize the automotive industry has garnered attention in countries like Japan and Germany, where hydrogen fuel cells are seen as crucial for meeting national emissions reduction goals. For example, Japan's hydrogen roadmap aims to have 800,000 hydrogen-powered vehicles on the road by 2030. Additionally, the replacement of gasoline and diesel fuels with hydrogen could significantly reduce the global demand for oil and other fossil fuels. This shift would contribute to diminishing the geopolitical leverage that oil-producing countries currently hold and could also lower global oil prices. Moreover, oil companies, which have long dominated the global energy market, would likely face significant challenges as alternative energy sources, such as hydrogen, wind, and solar gain ground. According to Bloomberg NEF, the global hydrogen market could reach $11 trillion by 2050. At the same time, the growing interest in hydrogen technology has intensified competition among automakers. Companies such as Toyota, Hyundai, and Honda are already leading the charge in hydrogen fuel cell development, with models like the Toyota Mirai and the Hyundai Nexo available on the market. Other automotive giants like BMW and Mercedes-Benz have also started to explore hydrogen-powered vehicles. This has led to a significant amount of research and development, with automakers investing billions of dollars into the production of fuel cells, hydrogen storage systems, and other related technologies. The transition to hydrogen-powered vehicles would also drive significant changes to urban planning and infrastructure. One of the most immediate shifts would be the establishment of hydrogen refueling stations. While conventional gas stations are ubiquitous around the world, hydrogen refueling infrastructure needs to grow exponentially to support a large-scale transition to hydrogen-powered vehicles. As hydrogen technology evolves, cities will need to integrate these refueling stations into their existing infrastructure. In dense urban areas, hydrogen stations could be built alongside existing gas stations, but in more rural areas, new distribution networks may need to be established to ensure a widespread refueling infrastructure. Refueling a hydrogen vehicle takes roughly 3 to 5 minutes, making it comparable to refueling a gasoline car, unlike EVs, which can take much longer. The rise of hydrogen vehicles also encourages broader urban mobility changes. With the potential to power public transport options such as hydrogen buses and trucks, cities could see cleaner, quieter, and more efficient transportation networks. Hydrogen-powered buses, such as those deployed in London and Hamburg, have already shown the potential for reducing emissions in public transport fleets. If this technology expands, entire fleets of city buses, garbage trucks, and other municipal vehicles could be transitioned to hydrogen fuel, making urban areas cleaner and more sustainable. The car that will destroy the entire EV industry. Now comes the part where we unveil the not-so-new player in town that is all set to shake the foundation of the entire EV industry. And that player is the Toyota Mirai. The Toyota Mirai, meaning future in Japanese, is a significant shift from traditional internal combustion engines and battery electric vehicles. First introduced in 2014, the Mirai marked a bold step towards mass-market hydrogen fuel cell electric vehicles. Its first generation prioritized functionality over aesthetics, offering a range of approximately 312 miles and relying on a polymer electrolyte membrane fuel cell stack. The second generation Mirai, launched in 2020, featured a striking luxury sedan design and an improved range of up to 402 miles. This iteration, built on Toyota's new global architecture platform, also incorporated enhanced safety features, better handling, and a more spacious interior, designed to compete directly with premium BEVs like Tesla's Model S. At the heart of the Mirai lies cutting-edge hydrogen technology. Its fuel cell stack generates electricity by combining hydrogen and oxygen, emitting only water vapor as a byproduct. Innovations in hydrogen storage include high-pressure, carbon fiber reinforced polymer tanks, ensuring both safety and efficiency. The second-generation Mirai further reduced the size and weight of its fuel cell stack, while boosting performance. Regenerative braking captures kinetic energy to enhance fuel cell efficiency, and high-durability materials extend the system's lifespan. Toyota's choice of hydrogen over battery technology reflects a strategic approach to addressing the limitations of BEVs. Hydrogen fuel cells offer longer ranges and faster refueling times, solving the critical issues of range anxiety and charging delays. Moreover, hydrogen can be produced from renewable energy, making it an environmentally sustainable option compared to the mining-intensive processes required for battery production. Toyota also sees hydrogen as a flexible energy carrier that can complement its EV lineup, diversifying its approach to achieving carbon neutrality by 2050. By leveraging its extensive market presence, Toyota is well positioned to popularize hydrogen-powered vehicles like the Mirai. The Mirai has the potential to disrupt the automotive industry, particularly in markets where Toyota has a strong foothold. Its ability to serve as a fleet vehicle, thanks to its long range and quick refueling capabilities, makes it an attractive option for taxis, ride-sharing services, and corporate fleets. Additionally, Toyota's commitment to hydrogen could catalyze investments in hydrogen production and refueling infrastructure. The Mirai's success also challenges the dominance of EVs, pushing other automakers to reconsider their hydrogen strategies and fostering competition and innovation in the field. With its environmentally friendly design, the Mirai could accelerate the adoption of green hydrogen, further reducing the automotive industry's carbon footprint. Despite its promise, the Mirai faces challenges, including the limited availability of hydrogen refueling stations and the high costs of hydrogen production and storage. However, as governments and private enterprises invest in hydrogen infrastructure and green hydrogen technology advances, these obstacles are likely to diminish. Toyota's persistent innovation, coupled with its ability to educate consumers about hydrogen's benefits, will be critical in overcoming these barriers. By championing hydrogen as a clean and versatile energy source, Toyota positions itself as a leader in the transition away from fossil fuels. The Mirai could revolutionize transportation, offering a cleaner, more efficient alternative to traditional and electric vehicles. Its success may not only redefine Toyota's legacy, but also shape the automotive industry's path toward a sustainable future. But it's not the automotive industry. Hydrogen adoption will change much more about the world as we know it. Broader implications beyond the automotive industry. Beyond the automotive industry, the role of hydrogen in renewable energy storage and its potential to reshape energy independence can transform entire industries, reduce geopolitical tensions, and create new economic dynamics. Hydrogen technology can serve as an effective medium for renewable energy storage, particularly for solar and wind power. While renewable energy sources like wind and solar have made great strides in becoming more efficient and cost-effective, they still face one major challenge: intermittency. Solar panels only generate electricity during the day, and wind turbines only work when the wind blows. This creates fluctuations in power supply that can destabilize grids if not properly managed. Hydrogen offers a solution to this problem by providing a means to store excess energy generated during times of high renewable energy output. Through a process called electrolysis, surplus electricity from wind or solar power can be used to split water into hydrogen and oxygen. This hydrogen can then be stored in tanks or pipelines and later used to generate electricity when demand is high or renewable generation is low. The stored hydrogen can be used in fuel cells to produce power, or it can be converted back into electricity in power plants, contributing to grid stability. For example, the High Balance project in Denmark and the Hydrogen Energy Supply Chain project in Japan are both working on integrating hydrogen into renewable energy systems. In these projects, hydrogen acts as a storage medium that helps balance the supply of renewable energy with the fluctuating demand. When there is an excess of renewable energy, such as on a sunny, windy day, hydrogen is produced and stored. During periods of low renewable output, the stored hydrogen can be used to generate electricity, essentially shifting renewable energy from times of abundance to times of scarcity. The European Union has already begun experimenting with this concept. The North Sea Wind Power Hub aims to connect multiple offshore wind farms, generating electricity that will be converted into hydrogen and stored for later use. By 2050, the EU hopes to generate as much as 80 gigawatts of offshore wind power, much of which will be converted into hydrogen to be distributed across Europe. This project exemplifies how hydrogen storage could become a crucial part of the global renewable energy infrastructure, enabling widespread decarbonization and reducing the need for fossil fuel-based backup generation. Hydrogen can also be used for heating and cooling in industrial processes. In high-temperature industries such as steel making, glass production, and chemical manufacturing, hydrogen can replace traditional fossil fuels to generate heat. Additionally, hydrogen can be used in fuel cells to produce electricity and heat simultaneously through combined heat and power systems, improving energy efficiency. For cooling, hydrogen's thermal properties and ability to power hydrogen-based energy systems allow it to support refrigeration and cryogenic processes in sectors like food storage and medical applications. As industries strive to meet stringent environmental regulations, hydrogen offers a scalable and sustainable solution to decarbonize heating and cooling operations while enhancing energy security. Hydrogen also has the potential to reshape global energy trade and geopolitics by offering countries a way to reduce reliance on oil-rich nations. Currently, the global energy market is dominated by a few key players, most notably the OPEC countries and nations with vast reserves of natural gas, such as Russia and the United States. These countries control much of the world's fossil fuel production and consequently wield significant geopolitical power through their control of oil and gas exports. Hydrogen, however, offers a path to energy independence for nations that do not have abundant fossil fuel resources. Countries like Germany, Japan, and South Korea, which lack significant domestic energy resources, are investing heavily in hydrogen production and infrastructure as a means to decouple their energy security from global fossil fuel markets. By producing or importing green hydrogen, which is made using renewable energy, and storing it for future use, these countries can reduce their reliance on oil and gas imports and become more self-sufficient in their energy needs. Moreover, the growing demand for hydrogen could lead to the emergence of new global trade routes. Countries with abundant renewable energy resources could become major exporters of hydrogen, offering new avenues for international commerce. The Australian hydrogen export industry, for instance, is already in development, with plans to export large quantities of hydrogen to Japan and South Korea, countries that are aiming to become major hydrogen economies. This shift could reduce the geopolitical importance of traditional oil-exporting nations, while enhancing the influence of countries that are leaders in hydrogen production. This shift could also affect energy diplomacy. As countries invest in hydrogen infrastructure, they may form new alliances and trade relationships based on hydrogen rather than oil. Nations that produce clean hydrogen could use it as leverage in global energy negotiations, similar to how oil-exporting nations currently use their reserves to exert influence. Hydrogen, as a clean alternative to fossil fuels, could also play a critical role in international climate agreements, with countries committing to a future powered by renewable energy and hydrogen-based solutions. Countries and industries that invest early in hydrogen technology may find themselves leading a new era of energy independence and geopolitical influence. This transition would also help to create a more resilient and distributed global energy network, one less vulnerable to the volatility of oil prices and the geopolitical tensions associated with fossil fuel resources. Hydrogen's potential to reduce intermittency in renewable energy systems and help integrate solar and wind power into national grids could unlock the full potential of these green technologies, accelerating the transition to a low-carbon economy. Last but not least, let's talk about money, the economic factor. When comparing the lifetime costs of hydrogen fuel cell vehicles to electric vehicles, the former tend to have higher upfront costs than EVs, primarily due to the complexity of fuel cell systems, including the platinum catalysts required for the electrochemical reaction. For example, a hydrogen vehicle like the Toyota Mirai or Hyundai Nexo costs significantly more than an EV like the Tesla Model 3 or Nissan Leaf, with prices often exceeding $50,000, largely due to the technology and manufacturing processes involved. However, when considering the lifetime costs, which include fueling, maintenance, and vehicle longevity, the economic picture can shift. Fueling costs for hydrogen vehicles are expected to decrease over time as the hydrogen infrastructure expands and production becomes more cost-effective. Hydrogen vehicles also benefit from shorter refueling times and greater range, offering advantages for long-distance travel or applications where downtime is critical, such as heavy-duty trucks and buses. Over time, the cost disparity between hydrogen and battery electric vehicles is likely to diminish as the hydrogen market scales up, driving down costs for both vehicle manufacturing and hydrogen production. A recent study by the International Energy Agency has shown that, depending on the region and application, hydrogen fuel cell vehicles could become more cost competitive than EVs in certain sectors by the late 2020s and 30s, especially as renewable hydrogen production becomes cheaper and infrastructure costs are amortized. Moreover, with government incentives and subsidies, hydrogen vehicles could potentially become more affordable for consumers. As of today, hydrogen infrastructure is still limited, especially compared to the widespread network of electric charging stations. However, projections suggest that with strong policy support and the economies of scale provided by greater market adoption, the cost of hydrogen infrastructure will decrease. Germany, for example, has already committed to expanding its network of hydrogen refueling stations as part of its national hydrogen strategy. If successful, this model could be replicated in other regions, driving down costs and boosting the commercial viability of hydrogen vehicles. As the hydrogen market develops, innovative pricing models may emerge to help make hydrogen more accessible and affordable for consumers. One possible approach is dynamic pricing, where the cost of hydrogen fluctuates based on supply and demand. This model could allow consumers to refuel at off-peak times, when hydrogen is cheaper to produce and store, and save on overall fueling costs. Another promising pricing structure is subscription-based refueling. Just as consumers subscribe to electricity or natural gas, they could subscribe to hydrogen refueling services. This model could include packages that offer unlimited fueling or tiered plans based on usage patterns. Subscription models may prove particularly attractive for fleet operators in the logistics or public transport sectors, where vehicles are consistently on the road and fuel consumption is predictable. With ongoing investments in infrastructure, innovative pricing models, and advancements in hydrogen production, the technology will help decarbonize various sectors, including transportation, industry, and energy storage. As governments, industries, and consumers work together to support this transformation, hydrogen may very well emerge as a driving force for a sustainable and prosperous future. Well, that's it for now. Thanks for watching. Did you like this video? If you did, please consider liking, dropping a comment, and hitting the subscribe button so that you don't miss out on our new uploads. Also, don't miss this video you see on your screen right now. It's truly unbelievable.